Hi, this is Matt, and I'm one of the co-founders of Complexica, and this is Unit 2 of a 6-unit video series for PRW that provides an introduction to the area of artificial intelligence. We will cover AI as applied to decision making in this video, followed by a detailed look at prediction, optimization, and learning, before landing on artificial intelligence in the context of the PRW environment, particularly as it pertains to the AI Foundations project. Again, there are two supplementary texts, The Rise of Artificial Intelligence, chapters 1 and 2, along with a case study called An Intelligent Decision Support System, which will be referenced in units 3, 4, and 5. In this video, we'll talk about the problem to decision workflow. We'll present it as a pyramid. We'll provide an example of each layer and also create definitions and separations between things that are typically confused or blended together. We'll show where artificial intelligence fits in and also provide examples of using artificial intelligence for decision making. Now, if you look at the problem to decision workflow, there are many layers between actually the problem and making the decision, some of which are available within an organization and some of which are not. The more of these layers are effectively implemented into any business, the greater will be the value unlocked, the greater will be the decision-making ability of those organizations. The bottom of the pyramid is the problem itself, and is probably the most important layer, because if we don't know what problem we're solving or addressing, then the rest of the layers don't make any sense. We don't know what data to collect, we don't know what to report on, we don't know what kind of exploratory analysis to do to discover knowledge, and so on. Common examples of problems are creations of promotional plans, reduction of inventory and working capital, creating production plans and schedules, predicting demand with some level of accuracy, restructuring sales teams to achieve greater results in the marketplace with the same resources, and the list goes on. Regardless of what problem we're addressing, what's important is that the problem is well defined, which allows us to then move to the second level or layer of the pyramid, which is data. Examples of data include employee timesheets, when someone checked in, when they punched out, did they take lunch, did they work overtime, pay slips or receipts from retail stores. This person went and bought a 6-pack of Coors Light from the beer store, whereas this person bought a whole shopping cart of alcoholic products ranging from Jack Daniels all the way to Maker's Mark. All of these represent pieces of data. In the PRW environment, you could have machine data, you could have sensor data, you could have data on transactions, on employee, on staff. They represent units of data that represent some value or attribute in terms of what occurred. The easiest way to think about information is as the aggregation of data. Information is often called a report or data summarization. In large organizations, they might have a business intelligence function, which is in charge of some centralized reporting and business intelligence tool where we can generate reports on what happened. Here is a visualization of revenue and margin realized over time. We could also run reports on inventory, what's our stock on hand, what's our stock value at a site over a period of time. We can also do the same with overtime for employees, by person, by site, over periods of time. All of these are examples of information, and they represent aggregation of data. In the PRW context, we could run production reports, we could run different reports on planned versus actual activities, reports on overtime, reports on what was produced and when, reports on machine failure, which is an aggregation of a variety of discrete data pulled together into a view like one of these you see on the screen. Now, the big difference between information and knowledge is information is concerned with what happened, whereas knowledge is concerned with why it happened. I like using this example of a report or a chart that shows historical sales data for one product. And it's a 6-week period. It's a chart that shows sales in hundreds of units, And what we can immediately see is how volatile the chart is, moving from 400 units to 1800, down to 800, up to 1600, and so on. This is a great example of information, of data visualization. And the difference between this and knowledge is that knowledge asks the question, why did this happen? What are these spikes attributable to? And knowledge discovery is usually a process of data analysis, of exploratory data analytics. And what we try to do is overlay certain data, like in this example, temperature, and look for relationships and correlations. And here we find a very strong relationship between temperature and sales of the product. When it's hot, we sell a lot. When the temperature falls, our sales fall as well. And this is consistently bore out through the whole data set when we overlay sales against temperature for the same period of time for the same area. This is an ice cream product or a variant thereof, and is strongly correlated to external variable weather in this particular case. There are other examples of knowledge representation. In a retail environment, we could do analysis around basket values and trends. If we're a store manager, we could also do an analysis of how our store pricing compares to other stores within the same network that we have access to pricing as well. And we could look for products where we have significantly overpriced versus the other stores in the networks, or significantly underpriced. We could also do knowledge discovery on over and under servicing within a retail environment. We could analyze times of high transaction and see how much staff we had on the floor, and then make an analysis to discover what were periods when we had a lot of staff on the floor but few customers, and what were periods of time when we had a lot of customers but very few staff on the floor, and then use that knowledge to make adjustments in our forward rosters and schedules. So this is a good example to show the connection between knowledge and prediction. We often use knowledge and discoveries that we've made through data analysis as the basis of predictive models that might be created. There is also, however, a major gap that exists between this part of the pyramid that ends at knowledge and the next part of the pyramid that begins with prediction. And this is attributable to the fact that knowledge, information, data, they represent the past. They represent what happened. Whereas prediction, optimizations, and the decisions that we're going to make represent the future. Where artificial intelligence sits is in the top part of the pyramid, and that is where the value is in terms of creating value in an enterprise. We're going to create value by making better decisions in the future, not by changing what happened in the past. Also, the area of prediction or optimization are areas usually of great complexity, and they are very well suited to artificial intelligence algorithms and methods. In fact, we can think of these top three layers of the pyramid together: prediction, optimization, and decision, and think of them as a decision optimization system. An application that can predict, can optimize, recommend a decision, and then learn from actual outcomes. So this brings us into the prediction layer, and one of the more classic prediction problems in business is that of predicting demand or demand forecasting. We take historical sales for a product, and then either manually or through a software system, we try to predict what sales will be in the future. In this particular case, a predictive model is making the prediction that even though demand has recently fallen off for this product, sales will snap back to a more normalized trend. The reason the predictive model might make such a prediction is because it considers more data than just the last 9 months. It would look at what happened in previous years in the same time period that we're now looking at. It might look at weather data, promotional data, pricing data, and other informational feeds that can inform the predictive model on what is likely to happen next. Also, when the future becomes the present, the system has the benefit of quickly uncovering whether its predictions were accurate or not, and learning from those and updating itself as it goes along. In this case, we can see that the original prediction made did turn out to be accurate, and demand has snapped back to a level that is very much in line with the original prediction. This problem of demand forecasting planning can be viewed in more modern software environments. This is Complexica's Decision Cloud, where we have promotions, pricing, demand, inventory, and business planning. And in the demand tab, when we load historical data for different products, this in conjunction with promotional information, pricing information, and external data sources allows the system to create a prediction of what we're likely to sell in the future. Another good use case and demonstration of predictive modeling, particularly within the alcohol industry, comes from trade spend optimization or promotional planning. We can select, first we need to go into the wine category, and once we are in the wine category, we can select Pernod Ricard as the supplier, and we'll pull up PRW wines. And on the PRW wines, we could create a promotional plan. Now, whatever plan we create, whatever it might look like, we could save it as a scenario, and we could then create further changes. And whatever changes we make, we can save those, and we could call this Complexica test. It'd be good if I spell Complexica correctly. Complexica test plan 1. And once we've created this plan or schedule, the role of a prediction model or engine based on AI is to take the plan that we've just created and tell us how it will perform in the marketplace. Make a prediction. Tell us if it's a good plan or a poor plan. Evaluate it. In this case, we're using a variety of different techniques that will be covered in later videos, but what is important is the output of the plan in terms of predicted KPIs like net sales revenue outcomes or volume outcomes and so on that we can report on as well. This is also a good point to talk about optimization, which is the next layer of the pyramid, because what we want to do is iterate that process that we just saw, create a plan, feed it to a predictive model, get a predicted outcome, and then repeat it. Keep iterating that plan. Create the next plan, the third plan, the fourth, the 10th, the 20th, the 100th, and search for a plan that gives us the best result. That is what optimization is all about. Instead of doing this manually, so if we go back into the slotting board and pick up, again, just Pernod Ricard products, let's find them here. So instead of manually creating these plans one by one, and for each particular plan creating promotions, we could create one for South Australia for this product, and this one for Queensland, do crazy stuff, and then save them, and let's call this the Complexica test plan 2. Go back to prediction. Here's my first test plan, here's my second test plan, here's some other ones that I've created, and then rerun the predictive model and have the predictive model show us what the results will be in the marketplace and compare them. And from this, pick the best result. You can the best plan that produces the best result. So you can see how we compare things side by side. Now, as you can see, this would be a very time-consuming process to go backwards and forwards between create a plan, predict the outcome, create the next plan, predict the outcome, and keep going until you find the best plan. So this is where optimization comes in. We pick just one scenario, and we tell the system that our main objective is to maximize volume, and then we ask the AI algorithms to do that manual iteration automatically for us. Instead of evaluating 10 or 100 or 1,000 plans, the system might evaluate millions. And it's working in conjunction with the predictive model to understand how each plan will perform in the marketplace, and then return to us the best plan, which not only is an improvement over the plan we had, but it shows us what changes were made. This is before, and then in blue optimized is after, and it shows us what changes the optimizer is recommending for us to achieve a better outcome in the marketplace. It also shows us how many changes have been made to our original plan, so that if we want to hold plan adherence or make a minimal number of changes, we can constrain the system to 3 changes or just 2 changes and capture this financial benefit. We have reporting on this before and after. We also have charting to show how volume increases, but fundamentally the role of optimization is to run all of these scenarios automatically for us in conjunction with a predictive model and find the one that best meets the KPI that we're trying to maximize in the marketplace. Which brings us to the actual decision. And oftentimes it's not as simple as just implementing whatever the optimization algorithms have come back with. The reason for that is because there might be trade-offs in making a decision. A classic trade-off is between inventory levels and customer service levels. On the one hand, we want to minimize our inventory and minimize our working capital costs, but that usually comes at the cost of service levels to customers. Metrics like fill rate or DIFOT. So there are actually many possible answers or plans that could be implemented to this problem, and each of them are optimal, but they trade off one metric against another. We can achieve a higher customer service level here, but it requires slightly more inventory and working capital than this one. We're not trying to make the decision. What we're trying to do from a software or artificial intelligence perspective is inform human experts of what this curve of optimality looks like, and depending on business objectives, the human expert can decide where they want to be on the curve for certain customers, certain products, certain geographies. The important thing is to be on the curve and not off it. Any solution that is, or plan or a dot that is not on this curve is suboptimal. And you can see why. This red dot involves a lot of inventory and working capital, and yet achieves a customer service level that's not any better than this. So from this position here, we could go left and dramatically reduce our working capital and inventory while holding the same DIFOT fill rate or customer service level, or we could go up and hold the same level of inventory but dramatically improve customer service levels. Decisions typically involve trade-offs, and that's why decisions are ultimately made by human beings, with machines and artificial intelligence algorithms doing the grunt work behind the scenes so that a human expert can make the best decision, an informed decision. If we go back to this Decision Cloud application and we click on the Inventory tab, we can go into Optimization, we can pick a scenario, and then we can define some maximum working capital, let's say 95 million, and some minimum service level, and the system will show us the trade-off between fill rate, which is at the bottom, the axes are reversed in this example, and working capital on the side. If we stop the optimizer for a second, we can see that we are presented with a number of possible solutions. Each of them is optimal. Each of them achieves a higher rate of either fill rate or lower rate of working capital, and the two trade off against one another. Hence, for this reason and others, making decisions isn't easy. And the last component is learning. Whatever decision is made, the actual outcome should be fed back into the application along with new data so that the system can learn. This is the same premise upon which human beings function and upon which the human brain works. We make predictions, or we have expectations, we make decisions, and then we get actual outcomes, and we see if our predictions or expectations have been met, and if not, we try to learn from that experience. Even if they are met, we still learn through reinforcement. the same process is created and embedded within software applications that are based on artificial intelligence algorithms and methods, so that the system is not static, but rather can actually adapt as circumstances change and continues to improve its own performance by recommending better and better decisions. That's it for this video, and in Unit 3 we're going to move into more granular subjects such as prediction, optimization, and learning using a case study around logistics in the United States.